Okay, I have started the recording. Let's begin with some announcements. Actually, first, a quick check on our system here. As you know, the lecture from yesterday, I had a little technical problem. I did upload it. I uploaded it in kind of an unusual way with the audio recording, faithful to the entire lecture. I didn't have the play-by-play antics on the chalkboard, but I did post a scanned copy of the chalkboard notes. Okay, so today we do have this thing recording, and we got the audio. So yep, things are looking pretty good for today's lecture. The first announcement. Tomorrow's lecture is going to unusual. This is affected by travel plans. Tomorrow's lecture, 9:10 in the morning to 10:30 in the morning. And of course, I will upload a recording. If that time is not convenient for you, you can watch the recording. It'll be in the video folder along with all the other lecture recordings. Here's the situation with office hours for the rest of the week. We got Thursday, 8 p.m. and Friday, 11 in the morning. Of course, that's looking ahead to the due date of the next homework assignment, which I vow to post later today. So currently you're working on a homework assignment that's due tonight. And then we have another homework assignment due Friday. We have to do that because next week there will be yet another homework assignment. And of course, Thursday of next week, the final exam. Also today, I'll be posting some details about which pages will be on the final exam. Okay, now we're in the midst of a discussion of the Hamiltonian formulation of mechanics. We have seen some examples where it appeared to be redundant. It appeared that we really don't need another formulation of classical mechanics, but in fact, there are some advantages to the Hamiltonian formulation. So what we're going to do is start by looking at some cases where the Lagrangian approach and the Hamiltonian approach are markedly different. Okay, we'll look at some interesting cases, and these are cases that relate to optics. Okay, so we're going to see how you can introduce a Lagrangian to describe the path of a ray through a medium with a non-uniform index of refraction. So think of a large slab of glass. Say you've prepared some glass, you have some molten glass, and then it cools down, and for some reason, the density is not a constant throughout this large slab of glass. What you have is an index of refraction here. The lowercase n is the index of refraction. Okay. Of course, we do not want to confuse this with the number of degrees of freedom, which is also lowercase n. We often use lowercase n, but it's clear from the context. This is the index of refraction. This notation indicates the functional dependence on the position. So we have the r vector as the position, and we're using lowercase s for arc length. So ds is a differential installment of arc length. And the product, as we commented last time at the end of our last meeting, the product of the index of refraction and the differential arc length is what is relevant to us. Apart from a multiplicative factor of the speed of light, this is what you need to integrate to figure out the time. We're looking at the total amount of time. If you want to travel from one location to another, traveling at the speed of light, and suppose you're free to choose any path, we're going to figure out how long it took traveling at the local speed of light. Remember, the speed of light in the medium is slower. It's knocked down by a factor of n, the index of refraction. So, of course, you could create really funny, loopy paths of light if you want to do that. Typically, they will not get you to the destination any faster. And so what we're doing here with this variational principle is that you literally could choose any path from a starting point to an ending point, and we compute the time it takes, again, apart from a multiplicative factor of c, which is a constant, it is this integral here. This is the integral we need to study. This is called the optical path length. If you deleted that index of refraction, it would just be the path length, right? If you integrate ds along any path, that per definition gives you the length of the arc, okay? So by including this index of refraction, right, it's the inclusion of this index of refraction that gives us the optical path length. This is what is relevant for the transit time for light. Okay, So the variational principle then applies to this integral. This, looking back to chapter 6 and 7 when we first started, oh no, I have to move this paper, sorry about that. Yeah, there's just so much on my to-do list. So yeah, the video feed of me is, some people do request that they can see the instructor. So that one is working, and the chalkboard, our beloved chalkboard, this is the one that gets recorded and uploaded. So yeah, yet another snafu, but again, this would not affect the uploaded recording. So we're covered in that regard. Now, the problem that we see here is this integral, because the integration is done with respect to path length, we've indicated two values, okay? If you have an arbitrary path, we're talking about ray optics, we're looking at the path of a ray of light through some medium, and we've selected 2 points by recording the s values, right? Those are lowercase s values. In contrast, remember, we used to, in chapter 6 and 7, especially chapter 6, we used capital S for this integral. Okay, we know that there's a problem here because we need to have the endpoints fixed, right? To carry out our prescription for the calculus of variations, we need the two endpoints to be fixed. So a simple reparameterization will cure this problem. So we have a remedy. We're going to introduce a parameterization. Notice we have fixed endpoints, 0 and 1. Those are kind of the quintessential fixed endpoints. So fixed in the sense of constant. Okay. And we have a parameterization, as we've discussed in the past, we have a parameterization. So let's put we're going to have an inset box here. Parameterization. Right, we've talked about this for our various path integrals. It's a mapping where a value lambda gets mapped to a point in space, which is r of lambda. Okay, so in the notation that's used by mathematicians, this is a mapping from the real numbers, and now they use an arrow with no serif feature on it, to a three-dimensional space. Okay, so that's our parameterization. We're really just interested in a subset of the real numbers, right? We're really just interested in this interval from 0 to 1. Okay, so having said that, we now have functional composition, right? This is really now n of r of lambda, right? A wonderful construction. We welcome any sort of nice functional composition like that. So we have the index of refraction evaluated at the location that we're currently at, and that's r of lambda. What's this differential arc length? Okay, you can convince yourself it is the magnitude of the derivative of this function. So that's the derivative. It's an ordinary derivative, dr d lambda, okay, times d lambda. Okay, so thinking of this as a parameterized path, you have a tangent vector, which is the derivative. Again, it's an ordinary derivative because this is a function of a single variable. And this product, which is the magnitude of that vector, right? That's the lowercase r there. Let me be clear. That's lowercase r. This is our ds. So what you see here, and we can liven this up with some color. This ds here is the product of these two things here. And look how I made that red line go through there. Okay, so having said that, what we're going to do here is we're going to extract a Lagrangian. This is a wonderful opportunity because you know what happens Thursday of next week. We've got a little ritual called the final exam, and we need to be very fluent with our calculus of variations. So let's take this opportunity to remind ourselves what it means to be a Lagrangian. Okay. You can read off from this construction that we have a Lagrangian and there is a Lagrangian here, which is the index of refraction, okay, as a function of position, times, let's write this out clearly, it's r prime dotted into, remember we like to prime for the ordinary derivative. We have this function, the ordinary derivative, notice those are regular d's. It's a function of a single variable, so we use regular d's. That's the derivative of this function. The more compact notation is r prime, and this is simply r prime dotted into r prime. Okay, now let's emphasize the structure here, right? One of the themes of the course is to appreciate the mathematical setting. And we can do that using our standard notation by saying the Lagrangian. Now we'll write, again, the same symbol, and this time we'll explicitly exhibit the arguments. This is the Lagrangian as a function of r, comma, r prime. Okay, so let's take a second to take stock of this. We're very familiar, right, and I'll write that here, compare. This will be another kind of inset box over here. Compare with what we do in mechanics. We often have a Lagrangian that's a function of a bunch of q's, and we write that as q vector and q dot. And there could even be some time dependence, but for the moment, we're happy without the time dependence, right? So the thing to observe here, and I'll put together a summary table in a moment, is the structure, right? We're very familiar, most of our mechanics problems have Lagrangian like this without the explicit time dependence. You have a Lagrangian, there are a bunch of q variables, generalized coordinates, and then you have the q dots. Okay, that's our usual picture with the Lagrangian for mechanics. For this optics example, we do have the same structure. We've identified a function here. It's a function of r, comma, r prime. Now this prime denotes differentiation. So here the prime differentiation with respect to lambda, right? That's the lambda. And here it's dot. So here the dot is the ddt. Let's use a different color. Dot is the time differentiation operator, ddt. And the prime indicates dd lambda. Okay, so there's that notational shift, but the structure is very important to us. Now the structure here is certainly not what we had in mechanics if you look at the actual function. Notice for one thing, it's a product. This Lagrangian is the product of two things. The first factor is the index of refraction. That's where you have all of the r dependence. The second factor is the magnitude of this velocity vector. Okay, it's just that vector dotted into itself, then you take the square root. That gives you the magnitude. Okay, it's remarkable that this Lagrangian gives you the correct answer. And first, before we go through the calculation, what is the correct answer? What's the correct answer for a light ray going through a non-uniform medium, such as a slab of glass with a non-uniform index of refraction? Okay, so let's take a second to talk about the correct answer, right? We're familiar with Snell's law. Good old Snell's law. If you have a swimming pool and a ray of light, when it reaches the surface of the water, there's some refraction that takes place. It changes direction. The generalization is the following. Okay, we have a generalized Snell's law. And the generalized Snell's law is pretty cool. Let's write it down, and we're going to show how the generalized Snell's law comes from this Lagrangian. So here's the generalized Snell's law, DDS. We got the gradient of the index of refraction. Here it is. Okay, that's the generalized Snell's law. You see, it's kind of a surprising result, and I would claim the average person out there is not aware of this generalized Snell's law. Actually, there are quite a few people who are aware of the standard Snell's law. Let's take a second to remind ourselves the usual Snell's law. We got the swimming pool, like so. We got the pencil ready to shade the water. This is the water. Okay. We have a reference line, like so, and we have refraction. Okay. Looks like I really made a mess of this diagram. Sorry about that. But you know the result, right? We got theta 1, we've got theta 2. We have an index of refraction, an index of refraction. The usual Snell's law is good old n1 sine theta 1 equals n2 sine theta 2. I did squeeze it in there, but I can do this like so. There we go. We got this in a box. It's a box within a box because this is an inset box already, like so. Yeah, this is just a reminder. We're talking about Snell's law. Here's the air, here's the water in the swimming pool, here's the refraction of a ray of light. So the usual Snell's law is expressed like this. Notice it's a sharp discontinuity. We have one value for the index of refraction here, it's a constant. Below, in the water, for example, if this is water, or let's take it up a notch. Let's say this is diamond, solid, huge chunk of diamond, okay? This is the law. It's an algebraic statement. It tells you the angle. We're going to see that you can deduce this law from the generalized Snell's law. So this is the generalized Snell's law. Okay, it is a little bit mysterious, right? But let's appreciate the next time you're looking at a sunset, this is what's working for you. First of all, let's talk about the gradient of the index of refraction, okay? The density of the atmosphere is greater the closer you get to the surface of the planet. So if it's over the ocean, we're talking about you're getting closer to the surface of the ocean, the density of the atmosphere is greater. So the index of refraction is greater when you get closer to the surface. And as you go way up high, so you get to the top of Mount Everest, the density of the air is about 1/3 what it is down here at sea level. Okay, that's pretty thin air up there. And you go even higher, it gets even thinner. So the point is, for our atmosphere, the index of refraction, though it's close to 1, right? It's just slightly greater than 1. But the point is, the index of refraction is greater when you get closer to the planet, and it gets smaller as you move away. Let's talk about the gradient of the index of refraction. The gradient of the index of refraction, the gradient of any scalar, it points in the direction of maximum increase. So next time you're looking at a sunset, just keep in mind the gradient of the index of refraction is pointing towards the center of the Earth, right? That's what we have here. Okay, and so this generalized Snell's law, it serves to steer the beam, okay? If you have a ray of light, notice everything on the left-hand side is kind of a glorified acceleration, right? If the index of refraction were constant, which it is not, but if it were constant, it would come right out, and you see you have kind of a second derivative of the position. This is kind of a glorified acceleration, right? So if the acceleration is pointing towards the center of the Earth, that's precisely what you see when a ray of light coming from the sun, it gets deflected slightly by the atmosphere. And this is important in astronomy. You know, when you're making precision measurements in astronomy, you have to have some sort of atmospheric model. If you're identifying the location of some amazing astronomical event, and say you're using optical light to record that event, then in fact, the location of that event in space is slightly at a different angle because the rays of light, they're getting refracted in a continuous manner. So the crucial thing here with this generalized law of refraction, right? Generalized Snell's law, is we have this smoothly varying, we have a continuous medium, and we can construct this thing, the gradient of the index of refraction. Again, the gradient of the index of refraction serves to steer the beam. So those are some remarks to make this plausible. This is a very plausible result, And we can actually do a calculation. If we have time, we'll do a calculation that if you have the air here and the water in the swimming pool, and if you imagine having a transition layer, a thin layer where we're going to smoothly make a transition from one value to another, then you employ this result and you recover Snell's law. So Snell's law follows from this generalized Snell's law, special case where you have an abrupt change in the index of refraction. And it's really nice because, you know, Snell's law can also be gotten from matching wavefronts. But notice there's no wavelength in this discussion. That's important here for our first, this is our first optics. We're going to have several optics discussion. This is our first optics discussion. And notice there's no reference to the wavelength of light. We're talking about ray optics. People talked about ray optics before they knew light has a wavelength. It's a little unfortunate we have lambda as our parameterization. This is certainly not the wavelength, right? You see it's a pure number that ranges from 0 to 1. It's just a parameterization of a path in space. Okay, so the remarkable thing is this Lagrangian is so simple. Notice it's just the product of the index of refraction as a function of position times the speed, right? Take the velocity vector, dot it into itself, take the square root, that's the speed, okay? And when I say velocity vector, that's kind of in quotes. We're differentiating with respect to lambda here, not the time. So it's really not the velocity vector in the usual sense of meters per second. Okay, so what we have here is a very clear function. It's a Lagrangian. It's a function of q's, right? With this structure, q's and q dots. And we can start computing partial derivatives. That's the name of the game here. There's the partial derivative of the Lagrangian with respect to this vector, like so. And when we write the partial derivative, I better make the arrow bigger. I see on the screen it's pretty small. Okay, hope it's not so small it's vanishing into infinitum or something. The prescription here is we must compute some partial derivatives. We're going to compute a partial derivative with respect to x, y, and z, right? And we're going to compute a partial derivative with respect to x prime, y prime, and z prime. We have 6 derivatives we have to compute. These are 6 partial derivatives. We group them and we put the arrow downstairs, right? That's a little bit unusual, but we've talked about this before. This is a time saver for us. So we're going to compute a collection of partial derivatives. There's the derivative with respect to x prime, y prime, and z prime here. All of that gets rolled up into a vector. And then there's the partial derivative of the Lagrangian with respect to r, like so. Again, this is a collection of 3 derivatives. We have the partial derivative of the Lagrangian with respect to x, the partial of L with respect to y, and the partial of L with respect to z. All of that gets rolled up into one vector, and that's the notation that is used here, this partial of the Lagrangian. So notice we can compute these quite easily because of the structure. This Lagrangian is the product of 2 functions. The first factor depends only on the position. It's just that n. So let's, without further ado, let's compute this. This one should be a piece of cake, as they say, very easy to compute. We're computing a partial derivative with respect to x, y, and z here. The second factor is simply a constant. In fact, it's more convenient to write it like so. So we've got the magnitude of r prime. That's simply a multiplicative constant. And then we have a collection of derivatives, right? The derivative of the index of refraction with respect to x, y, and z. And so that would be, in this notation, we'll just write it as partial n partial r. Okay. But that partial n partial r really is the same as a gradient. You see, these two are identical, and therefore I must squeeze it in over here. I'm going to just emphasize it's a question of notation. This gradient, the gradient of the index of refraction, that's the most popular notation. But using the notation here, let's just be clear, this is identical to the partial derivative of the index of refraction with respect to the r vector. And yes, I have, if I can get this arrow in there, I'm done squeezing the, yeah, I think I did it. Okay, let's just observe that that's a question of notation. The more popular form is to write the gradient The index of refraction is a scalar, right? So this is the gradient of a scalar, but we must make a connection with our notation here. So we've done that derivative there. Let's compute this other partial derivative. We need the partial derivative of the Lagrangian with respect to r prime. Okay, by the way, let me ask you this. If you notice any problems with the audio, maybe send me a message in the chat, because that would indicate a problem with my internet connection. If there's a problem, I might be able to fix the problem using a bunch of tricks, okay? But I believe, for me, the important thing is if I move the pen, I can see it move on the screen. That's accomplished with this iPad Pro. It's a participant, it's the document camera, it's a participant in the meeting. And if that participant is sending that image to my laptop, we have the connectivity. So that's my first measure. It's like a thermometer to assess the wellness of a patient. I believe we have a good connection. When the pen freezes momentarily, that's what worries me. But I believe the Zoom technology puts the audio at a higher priority. So I think the audio hopefully came through. Let's compute this partial derivative. It's a partial derivative with respect to r prime. And this is a construction we've done before. Notice you have the square root, so we have a quantity raised to the 1/2 power, and then you have the vector dotted into itself. So we're going to copy over this prefactor, that's the n of r. Okay, and then we have a few more things to do. Just to let you know, the result here is going to be rather surprising. We're going to see that the usual prescription, right? We had a prescription for how you produce a Hamiltonian if you have a Lagrangian function. The usual prescription is going to be unsuccessful here, and let's appreciate why it's unsuccessful. But to be clear, the Lagrangian formulation here is correct, and I must finish this calculation here. So the partial derivative of the Lagrangian with respect to r prime is this multiplicative factor n of r, that's a constant. And then we must differentiate this. It's a quantity to the 1/2 power, so the derivative is 1/2, okay? We have the quantity to the minus 1/2 power, so that's a 1 over the square root of the r prime vector dotted into itself. And then we must differentiate what's inside here with respect to, imagine one of these, for example, x prime. And what you have there is, the upshot is this becomes a 2 r prime vector. Okay, so that's a collection of 3 items. They're rolled up into a vector. Again, you should think of these as being individual calculations. So when you differentiate with respect to x prime, that will be the first element of this vector. We must read the first element of this vector here. That's the 2x prime, and that's the derivative of this quantity inside the square root with respect to x prime. Okay, so that gives you a feeling for the kinds of calculations that are involved here. Now here's the important thing. We have to budget our time. So we'll just briefly state that the Euler-Lagrange equations now in this context tell us that the total derivative, and now we're using lambda as the parameter, so it's the total derivative with respect to lambda of this partial, like so, and that's the prime there. I want to emphasize that. This is equal to the partial of L with respect to the R vector. So these are the Euler-Lagrange equations. I'll just write that over here, Euler-Lagrange. Okay, so there's a little bit more work to be done, but again, let's budget our time, and also let's be very clear. We're in the midst of 3 discussions of optics. We're talking about optics and a Hamiltonian formulation for optics, okay? This stuff is not on the final exam, okay? This stuff is not in Taylor, and it's not on the final exam. It's useful for us to discuss this. We get a better understanding of the Hamiltonian formulation. We get some wonderful opportunities to review the Lagrangian formulation, so that's what we're doing here. But I want to be very clear, this stuff is not on the final exam. It is kind of, let's think of it as a special treat. We get to talk about some optics and, you know, applications to laser physics, things like that. Okay, so there's some more effort here. There's a certain reparameterization, but let's just go straight to the conclusion. If you write out this Euler-Lagrange equation, You see the reparameterization that occurs. We just have to reparameterize from lambda to s, etc. You do get the generalized Snell's law. So in summary, what have we done here? We've used this variational principle that's been known for a couple hundred years. We have a variational principle. Once you write down the integral, and this is the integral for the optical path length, then you read off the Lagrangian. So we read off the Lagrangian. Here's the Lagrangian. We employed the technology we have from the calculus of variations. It tells us to compute some partial derivatives, and then it tells us to compute a total derivative, etc. We did all that stuff in principle. We skipped the details here in lecture today, but just let the record show it delivers this wonderful result, the generalized Snell's law. So we have this generalized Snell's law. Okay, in summary, the Lagrangian formulation is successful. Now, we're in chapter 13. We would like to see a Hamiltonian. Here's where we have a real shocker. It's impossible to get a Hamiltonian from this Lagrangian. Okay, that's a little bit disappointing, but worry not. We're going to have another Lagrangian formulation which can successfully produce a Hamiltonian. And then we'll even have a third optics discussion, a wonderful covariant optics discussion. Okay. So here's the summary. And it's useful to have a direct comparison, right? One of our objectives here is to prepare for the final exam. Okay, so here is an overview of where we're going. The stuff you do need for the final exam. Let's have that be very clearly stated here. What you do need for the final exam is the, let me put it like this, and I got a little issue over here. Let me scoot that thing over there like so. All right, much better. So what you do need for the final exam, the Lagrangian formulation of mechanics, right? So in this table, I like to write the capital cursive L for one thing, and also it's a time saver. I don't have to write Lagrangian. So Lagrangian mechanics this is one of the things you need for the final exam, right? That's going to be the first column here. Okay, Lagrangian mechanics. Now this discussion we had up here on this piece of paper, we're going to call that our first optics discussion. We're going to have 3 optics discussion. Our first optics discussion. Okay. And then there will be 2 more. There's going to be a second optics discussion. Each one of these very exciting, an exciting discussion unto itself. And then there's even a third optics discussion. Okay. So this is kind of the big picture. As we explore the wonderful world of Hamiltonians, let's be clear on what's going on. So first of all, what is the Lagrangian? Okay. Well, in Lagrangian mechanics, let's assume there's no explicit time dependence for a moment. For the moment, here we go with a pretty generic Q and a Q dot like so. So what this is saying is you have a bunch of degrees of freedom, could be 3, could be 100, etc. All those Q's, Q1 through Q little n, those are assembled into a vector here. And here's a collection of Q dots. So this is the usual kind of Lagrangian. This is the kind of thing we're responsible for on the exam. In this first optics discussion, we had a Lagrangian, and this was our Lagrangian here. You see it's a function of r and r prime. So there's a slight shift in notation. That's the point of this comparison table. We do have this shift in notation. Okay. Okay. The parameter of evolution. Okay. Remember, this first column is what we really want for the final exam. We want to do physics, in particular mechanics, right? We're interested in mechanical systems. We would like to know the position, the evolution, the configuration as a function of time. So we're interested in the time evolution. Now for this first optics discussion, the parameter was lambda, okay? I just mentioned that it's useful as you look at these equations, etc. Here's this dd lambda, right? That's because lambda was our parameter of evolution. And it's useful to make this comparison. Here's the time t. Okay, what can we say about the velocity? Okay, in mechanics, we would talk about the time derivative, and we write q dot like so. Q dot is the time derivative when you solve the system. This would be the total time derivative. When you solve the problem, total time derivative, and it's a function of time like so. Okay. Here in this topics discussion, we had the so-called R prime, right? We used prime for differentiation. That was the derivative with respect to lambda. There was just one independent variable lambda. So our usual notation is this prime like so. And again, this was our derivative with respect to lambda. Okay. Okay, next, the momentum. Okay. This is important here as we work through chapter 13. Remember, this stuff here in this first column, this is what's really important to us. So the momentum is defined in the following way. Sometimes we write this with an index, and sometimes we like to collect it into a vector. So when we write the p vector like so, this is a partial derivative of the Lagrangian right? There's a time and a place for this notation, right? The arrow is very useful to convey that there's a free index. Typically, we would write this as p sub I is the partial derivative of the Lagrangian with respect to qi dot. That index I is a free index, so you can express it with this arrow. So by introducing this arrow notation, we have a vector on the left. That's just a collection of p1 through pn. And over here, we have a vector on the right. It's a collection of partial L, partial q1 dot, all the way up to partial L, partial qn dot. Okay, that's the momentum. Okay, in optics, they don't like to use P for a momentum. They like to use K. That's just the way it is in optics. People call it K. It's a so-called wave number. If you have a plane wave, for example, you have this K vector that's perpendicular to the wave. It's the familiar K vector. And this is the partial of the Lagrangian with respect to this R prime vector. Okay, so you see it's the same structure. That's the important thing. Again, it's that first column, Lagrangian mechanics, that's what we're responsible for the final exam. And what we're illustrating there in that first column is the principle whereby you construct the Hamiltonian. If you have a Lagrangian, you can construct the Hamiltonian from it. And this is a formula for success, right? The Hamiltonian is gotten by a multi-step process. The crucial thing is you solve for the velocity. So solve these equations here, these momentum equations, you solve them for the velocity. Okay, so we solve for the velocity. What does that mean? You have a qi like so, and it is a function of q's and p's. Remember, that's the crucial, this is a crucial milestone in the Hamiltonian formulation. This box here denotes a collection of equations. We view that as a huge algebraic chore to solve for the q dots. When you do that, you have some sort of formula. Qi dot is a function of all the Q's and all the P's. Okay, that's a bunch of algebra. Okay, once you've done that, you can construct the Hamiltonian. Okay, so then construct Hamiltonian. Okay, so what we're seeing here on the left, this multi-step process, you know, we have a formula. The Hamiltonian is constructed once you have this setup. You have the P's dotted into the P vector, dotted into the Q dot vector, minus the Lagrangian. Okay, so here's the problem. With our first optics discussion, we have some terrible news here. We do have the momentum. Unfortunately, there's a no. It is impossible to solve. It's impossible, and we'll show why it's impossible. But we'll have a second optics discussion, which there's a yes here. Okay, that's going to be our second optics discussion. Okay, so yes, it's an interesting story. Again, the optics discussions are there to broaden our horizons. We like to see how the Hamiltonian formulation can be used in other branches of physics. At the same time, we're going to cement our understanding. This stuff here, right? This first column, this is crucial for the final exam. You have to understand this stuff. Okay, so as we go through this, let's appreciate, right? And when we hit this big dramatic all caps no, when we hit this stumbling block, it will help us to understand what's going on quite generally with this process whereby we solve for the velocities. And over here, it's going to be a yes. All right, that's going to be a lot of fun when we get there. All right, so let's revisit our discussion here. Why is it impossible to solve for the velocities? Okay. So this is our first optics discussion. We successfully computed this partial derivative. We successfully computed this other partial derivative. We wrote out the Euler-Lagrange equations. It was a wonderful, successful story thus far. Okay. But can we solve for the velocities? Let's look at that question here. Okay, let's examine that very important question. Can we solve for the velocity? So again, this partial derivative of the Lagrangian with respect to the velocity, this is what we call the momentum. Okay, that's the momentum. We would call it P in the classical mechanics, but in optics, they just insist on calling it K. So let's call it K, just so these notes are compatible with any standard text on, for example, Born and Wolf, wonderful text on optics. Okay, so we have this nice equation, and can we solve this for the velocity? What you have here is the velocity divided by the magnitude of the velocity. I want to emphasize that. There, the 2's cancel out very nicely, and this is a unit vector tangent to the velocity. So it's tangent to the curve. A unit vector tangent to the curve, it points in the same direction as the velocity. So let's take this equation, write it down again over here. I should say way down here. And what we have here is that the momentum K is equal to, you see the index of refraction? Okay, and this is the velocity vector divided by the magnitude. Okay, so first a quick sanity check in terms of optics. This is saying that the K vector, it points in the same direction as this. Remember, the velocity vector is tangent to the curve. We have a ray of light. It's going through some medium. Okay, it's tangent to the curve. So the K vector points in that, and it has a magnitude. The magnitude of the k vector is the index of refraction. This is a unit vector here. So for this discussion, the k vector is dimensionless, and the magnitude of the k vector is the index of refraction. Okay. So when we say solve for the velocity, what does that mean? Well, if somebody gives you a value for a k vector, can you determine which value for the velocity vector, that's the r prime vector, should you use? And the answer is no, because you cannot solve this. The reason is this construction here throws away information. Okay, now we have a big, okay, the document camera is working in, but it's kind of slow. I'm watching, okay, now we're fully functional. I'm watching the document camera. So by its very nature, this construction throws away some information. We have the velocity vector divided by its magnitude. You compute the k vector, but you cannot invert this. So another way to say it is, we'll write it down here. Let's compute the magnitude of both sides. Well, you have the magnitude of k. The magnitude of the momentum is equal to n of r, right? Because this quotient is a unit vector, right? So the magnitude of that is 1, it's unity. And it is independent of the velocity vector. Oops. Let me delete this, sorry. That vertical bar's got to go. So the magnitude of the momentum vector is equal to the index of refraction. It's independent of the velocity vector. In particular, it's independent of the magnitude of the velocity vector. I mean, I think we can see here the velocity vector and the momentum vector, they point in the same direction. The only remaining task is adjusting the lengths. But from this formula, you cannot determine the length of the velocity vector. Okay, so in summary, we have this very big, it's all caps, it's no. This one is a no-go, it's not gonna work. Okay, so it's a no here as well. Okay, so in summary, the first optics discussion was successful. We got a Lagrangian, we got the correct differential equation that governs the motion of those light rays, the motion that's, so to speak, the path of the light ray through the glass. All of that's correct. We got generalized Snell's law. However, we cannot get a Hamiltonian. So that's interesting. We have a successful Lagrangian, but we cannot get a Hamiltonian. So let's look at this second optics discussion. We can get a success, we can get a Hamiltonian in this second optics discussion. Okay. So here's our second optics discussion. Okay, and this second optics discussion, again, we will see some interesting connections with the Hamiltonian formulation of mechanics. Okay, what we're going to do for the second optics discussion, we're going to break the symmetry. Okay, and we'll choose z, the z coordinate. All right, so let's draw a picture. Here's our familiar XYZ coordinate system, okay? It's intended to conjure up an image of a three-dimensional space. We're going to assume that the path, I'll use a different color. We're going to assume that the path looks like this, so we will use z as the parameter. Use z as parameter. Okay, this is the crucial thing here for our second optics discussion, is we're going to use the z variable as the parameter. So we're going to solve for x as a function of z and y as a function of z. Okay, so this is crucial. Let's take a moment to make a connection, right? We always like to make connections between different parts of the course. Remember in chapter 8, we worked out a formula for the shape of the orbit. Ellipse, hyperbola, parabola, right? Those are some examples for the Kepler problem. The point is, we had a formula for the shape of the orbit. So I'll put compare. In chapter 8, we had this wonderful formula for r as a function of phi. Right. Okay, so that's the important comparison here. We know this is a very important, this is in the chapter summary, it's very useful for solving problems. That formula, that gave you the shape of the orbit. It did not tell you how quickly or slowly the particle went around the orbit, but it told you how to draw a picture of the orbit. It perfectly defined, if it's an elliptical orbit, this formula tells you how to draw that ellipse. So in the same spirit, these formulas here, we have x as a function of z, y as a function of z. These tell you the shape of the path, and a nice example here would be this red curve. It's kind of like in relativity theory, you speak of the world line. It doesn't loop around back on itself. So in principle, if you have a non-uniform medium, a ray of light can loop around. Not a closed loop, but it can do some interesting things. Actually, you could even arrange for a closed loop with proper crafting of the index of refraction. Okay, so here's what's happening with our second optics discussion. We use z as the parameter. So our goal in life is to find x as a function of z and y as a function of z. These two things we're going to call r perp. So here's this little symbol that's like a little symbol to indicate perpendicular. And so this is a two-dimensional space perpendicular to the z-axis. So again, x of z and y of z, we're going to call that r perp. That's the perpendicular space. It's perpendicular to the z-axis. Okay, so what we'll do here is we'll just jot down the optical path length. Remember OPL. We like to talk about the optical path length. When in doubt, if you're ever on a job interview or something and they're asking you, just start talking about the optical path length. You're guaranteed to impress people with that. Integral from z1 to z2, we have the index of refraction as a function of position. And then this construction, remember all those fond memories from chapter 6. Now it's a 1 plus the magnitude of the r prime perp squared dz. Okay, so this is a familiar construction from chapter 6. Think for a moment about taking this dz, putting it inside the square root. Then that 1 becomes a dz squared, and this r perp squared thing is a dx squared plus a dy squared. So you see that's that square root by Pythagoras gives us our differential arc length. So again, this thing here, this entire thing is ds. Okay, so that's the optical path length. You get a Lagrangian. We're going to have to skip the details here because of our extremely challenging schedule. But the point is you can read off a Lagrangian. Okay. There are various calculations to be done here. You can get a Hamiltonian. In the notation here, the Hamiltonian is equal to, there's a perpendicular k, right? It's that two-dimensional space, sorry. And we're going to dot that into the velocity, that's the r prime perp, and then subtract the Lagrangian. Okay, so that's our second optics discussion. We'll just put yes like this. And so we won't fill in these boxes. I gave an overview of the discussion there, but we really do have to budget our time. Let's just appreciate that's a formulation for ray optics in a medium with a non-uniform index of refraction. Okay, let's talk about our third optics discussion. It's a wonderful discussion. All right. This third, okay, we have a question in the chat window. Let me get the chat window here like this. Okay. The very last bit of the last page. Yep. So yeah, we have a question in the chat window about this part here. This last part was how we get the Lagrangian. You get the Lagrangian like this. Okay, so that Lagrangian is a function of the perpendicular. There are these two perpendicular variables, x and y, these two variables here. So that's the r perp and z. Okay, notice this z here is kind of like the time t, because in our comparison, the parameter of evolution now is z. Okay, and so our Lagrangian looks like that. So this Lagrangian, okay, this Lagrangian is actually a quote. It's quote time dependent. Of course, this is not really the time, it's z. And z is one of the three physical axes in our physical space. But we've chosen to describe the shape of this curve, this red curve here for the ray of light moving through the non-uniform medium. We've chosen z as our parameter of evolution. And this is x comma y, x prime comma y prime, and z is the parameter of evolution. And so you can read off the Lagrangian from the, right, it's n of r. Okay, so yeah, it's useful to review this. Remember, the basic philosophy is you have an integral, and to put it, okay, I see there's another question in the chat window. Just let me finish this here. To put it succinctly, you set up an integral for something you're trying to minimize. Let's just use minimize for simplicity. We'll use the word minimize. You look at that integral, everything except for the differential, in this case is dz, everything except for the differential is the Lagrangian. So that's how you get this Lagrangian. Notice it is a function of, here's the z dependence. That's x comma y comma z. X comma y is here, z is here, okay? And then you have this, okay, now there's a question in the chat window. The other page, okay, that was this page here. Yeah, so we have the definition of the momentum. In optics, it's called, so in mechanics, this would be called P. Right, in mechanics, that's called P. In optics, they call it K. And the definition of the momentum, the generalized momentum, you take the Lagrangian, you compute the partial derivative with respect to the velocity. So that was this calculation here. The 2's canceled out very nicely for us. And now we have the velocity vector, which is r prime, over the magnitude of r prime. So that's this, this formula here, right? The square root of r prime dotted into r prime is the magnitude of r prime. In the numerator, we have the velocity vector. I just copied that over here. So this formula tells you the momentum if you know the velocity vector. It's a prescription, right? So if you use this formula in the following sense, given a velocity vector, you can compute the momentum vector, right? It's a prescription. If somebody gives you a velocity vector, you compute the momentum vector. Can you go the other way? And the answer is no. If somebody gives you a value for the k vector, you cannot uniquely determine this velocity vector. Okay, the situation is if somebody gives you a value for the momentum vector, it will either be true or false that the magnitude is equal to n. If the magnitude is not equal to n, then there are no solutions for the velocity vector. If the magnitude is equal to n, then there are infinitely many solutions for the velocity vector. In either case, we don't have a unique solution. We don't have a clear formula for this inversion. So we cannot solve okay, so that's that's kind of a summary of this portion of the page. Yeah, great question. So if you have further questions, let's discuss that in office hours because we need to move on with our lecture schedule here. Okay. So the third optics discussion is a remarkable thing. We're going to look at a covariant Hamiltonian. So here's this third optics discussion. Yeah, wonderful stuff, the whole world of optics. So here's the third optics discussion. Okay, and you know, physicists love to use this word. We have a covariant Hamiltonian. Okay, let me position this like this. We're going to start with a covariant Hamiltonian. Okay, and so this Hamiltonian, remember, it is a function of Q's and P's in the language of physics. So in the language of optics, we have X, Y, and Z here. These are kind of like our generalized coordinates. And here's the momentum vector. Okay, so Q's and P's. And this is just what you would call omega of R comma K. Okay, so what is this? It's the speed of light times the magnitude of the K vector over the index of refraction. Okay, so let's contemplate what a wonderful Hamiltonian this is. Notice the construction. The Hamiltonian must be a function of coordinates and momenta. So that's the prescription here for the Hamiltonian. We have coordinates, we have momenta, and here's the formula. This is kind of an optional remark here with the omega. Let's return to that in a moment. But here's the prescription. Again, it's a wonderful construction. Notice how simple it is, just the magnitude of the momentum vector times the inverse of the index of refraction. In that sense, it's similar to the Lagrangian. Remember, our first optics discussion had a Lagrangian that was a product of two things. The first factor was this index of refraction in the numerator, and the second factor was the magnitude of the velocity vector. So here's this Hamiltonian. You can write out Hamilton's equations. This gives us an opportunity to talk about Hamilton's equations. So here we go with Hamilton's Hamilton's equations. In this notation here, we have dr dt. So that's a collection of three equations for the Q variables. Dr dt equaling the partial derivative of the Hamiltonian with respect to the momentum. So again, we're using the vector notation to encapsulate three equations. There are three equations here. The first one is dx dt as the partial of the Hamiltonian with respect to kx. The next one is dy dt equaling the partial of the Hamiltonian with respect to ky, and dz dt equaling the partial of the Hamiltonian with respect to kz. So these are certainly three of the Hamilton equation. The other ones are dk dt, and here we got the minus sign, minus partial h partial r. Okay, so these are Hamilton's equations. And these are things you can readily compute. So what's the partial derivative with respect to k? That's a calculation we did earlier today with different notation. All right, so for that calculation, we have a constant c over n. That's simply a constant. And now we have the magnitude of the k vector. So this is a calculation we did earlier. When the smoke clears, so to speak, you have a cancellation of a factor of 2, et cetera, and so forth. You clean it up. You get the k vector divided by the magnitude of the k vector. Okay, so far so good. And the other equation, when we compute the derivative with respect to r, there's only one case where that occurs, and that's right here. Okay, So we get the CK magnitude over n squared. Notice the minus sign here gets canceled because we have n to the minus first power. When you differentiate n to the minus first power, you get minus n to the minus second power, and then the gradient of n like so. Okay, so it's possible, we're going to skip the algebra. We don't have time for the algebra. You get the generalized Snell's law. Okay, so that's I will post the lecture notes, right? You can read about this in the lecture notes. It gets a little bit messy, but the point is we can set up a Hamiltonian formulation for the optics. Okay, so again, let's take a second to summarize. This has been a fascinating excursion into the world of optics. We have seen Lagrangians, we have seen Hamiltonians in the world of optics, and we saw that it was very useful. We have this nice summary table here. For this third one, we did get a Hamiltonian, like we started with the covariant Hamiltonian. Okay, but remember, our goal, looking ahead to Thursday, let's do this. This is what's important to us, appreciating this prescription, okay? So in today's lecture, we're now going to continue with mechanics. We're going to continue with this box here, the Hamiltonian formulation of mechanics. Okay. It has been asked, and rightfully so, why should I care about the Hamiltonian formulation of mechanics? So let's start explaining some of the wonderful things about the Hamiltonian formulation of mechanics. Canonical transformations. Okay, we're going to see that there's a huge class of transformations that preserve the structure of Hamilton's equations. In fact, we're going to enjoy a far greater freedom than we had with the Lagrangian formulation. Let's compare. Let's compare the following. Okay, so again, I'll use the cursive L and the cursive H. In the Lagrangian formulation of mechanics, we had the notion of generalized coordinates. Okay, and we typically use the variable q for one generalized coordinates. If you have several generalized coordinates, right, this is a convenient notation. Lowercase n indicates the number of degrees of freedom. Again, we're assuming holonomic constraints. So we can just enumerate a list of these generalized coordinates, q1 through qn. And it's convenient. You see how much time you can save by just introducing a vector. Q vector, that's the collection of these coordinates. Okay, so there's our generalized coordinates. And we know that you can transform the Lagrangian. So for this discussion, we use capital Q. This is a new choice, okay? And again, our notation is to emphasize the functional relationship. Okay. So this is a transformation. We've introduced a new choice of generalized coordinates. So you can transform to the new coordinates, capital Q. Okay. In the Hamiltonian formulation, there's a larger class of transformations. Okay. So what we're going to do here, we'll introduce, here's the capital Q. Again, these denote the generalized coordinates. It's a collection. Again, the index goes from little, there's that little 1, there's that little n. You should imagine the same thing here, capital Q1 through capital Qn. And furthermore, there's going to be a capital P, which I'll indicate with the serif feature like so. There's a capital P. Okay, let me take a second to move this chat window here. Okay, great. All right, so here's the wonderful world of the Hamiltonian formulation, and you can define the capital Q's like this. Here we go. Okay, we're going to be interested in the definition of these new capital Q's, and they are allowed to be functions of the Q's and the P's. And furthermore, this is the meaning of this notation. When we say P is equal to P of, you read that by saying capital P is a function of the lowercase q's like so, and the lowercase p's like so. Okay, so this is called a canonical transformation, this thing here. If Hamilton's equations are invariant, so let's write that like this. Okay, so let's work out some examples. Let's see how you can actually set up a canonical transformation and transform. Okay, so here's an example. Okay, this is for a 1 degree of freedom problem. So this Q vector will simply have one generalized coordinate, and we'll just call it Q. So to summarize, we'll simply drop the arrows. Okay, so for 1 degree of freedom, you just have one generalized coordinate, Q1. There's no need to have that 1 on there because there's only one Q. And so we can even drop that index. That's equivalent to saying we're going to drop this arrow. Okay, so here's how we'll define this transformation. The lowercase q's are related to these capital. And remarkably, you're going to need this factor of 2. There's a factor, it's actually the square root of 2. Okay, so this is the one direction. Let's put a box like so. We're going to describe both the forward transformation and the backward transformation. Here we go with the other direction. So capital P, you see how my capital P looks like this. The lowercase p is clearly distinct from the capital P. Right. And notice the choice of units. We've absorbed, if you think of the simple harmonic oscillator, for example, we've essentially set the mass and the spring constant equal to 1, because if you have q squared plus p squared, it means that q and p have the same dimensions. Okay, so this is kind of an idealized discussion where we've absorbed those constants. All right, and furthermore, the tangent of q is little q over little p. Okay, so here's the transformation. Notice this box, if you have the lowercase variables, if you have little p and little q, you can compute the capital variables. Here you need to do an arctangent. In this box, if you have the capital variables, capital P and capital Q, you can compute the lowercase variables. So you see it's very similar to plane polar coordinates. The only difference is we have the square root of P here, right? You're familiar with plane polar coordinates. There's an angle. We usually call it phi in Taylor's book, and there's a radial variable, lowercase r. But here it's very important that we have this square root. We're going to see that that's essential to have this transformation work out. Okay, so let's start computing some derivatives. So what can we say about q dot? Okay, so q dot, we're going to compute the total time derivative. Remember, we like to use the dot for the total time derivative. Here's the formula. We must compute the total time derivative. So there's a function of time, capital P, and there's another function of time. Here we go. We have the square root of 2. All right. We have P raised to the 1/2 power, so that's going to be a 1/2 capital P raised to the -1/2 power. And then we must differentiate capital P, so that's the capital P dot. Okay. And this is the first term, so we copy over the sign Q, right? We're using the product rule. Now, the product rule tells us there's going to be another term. You copy over the first factor, so that's the square root of 2 times capital P. Okay. And now we must differentiate the sign of capital Q. That's the cosine of capital Q times capital Q dot. Okay, so far so good. Very similar for this thing here. We have the lowercase p. Let's differentiate it. Okay, again, it's the total time derivative. Very similar structure, especially this part here. We have the root 2. We have the 1/2. We have capital P raised to the -1/2. We have the capital P dot. And now it's the cosine. We copy over the cosine. Okay. And then we have this square root of 2p. Now we have a calculation where this is constant. We're differentiating this cosine of q. So that's going to give us a minus sine of q. And there's the capital Q dot. Okay, let's take a moment to rewrite this. It will behoove us to rewrite this equation. And you know we love matrix multiplication, so let's observe that these two equations can be summarized very nicely. Okay. We love matrix multiplication, right? Notice this is a rotation matrix. Times a diagonal matrix. Uh-huh. 1 over square root of 2p. Okay. So now we have worked out the relationship between the lowercase q dot and p dot and the capital Q dot and p dot. Okay. There's still some more work to be done here. Okay. We're going to transform the Hamiltonian. This discussion is for an arbitrary 1 degree of freedom problem. So there's some sort of Hamiltonian. Okay. And now we'll define a new Hamiltonian for the new variables. This is logically distinct. It's a distinct function. So this new Hamiltonian, it's a function of capital P and capital Q. You plug into the original Hamiltonian. So this, the capital script H with no further decoration, that's the original Hamiltonian. And we plug in the square root of 2p, right, with the sine of q, comma, the square root of 2p, and here's the cosine of q. Okay, so that's the transformed Hamiltonian. What we're going to do next is calculate these partial derivatives. So what's the partial derivative of the new Hamiltonian with respect to capital Q? Okay, notice what we have to do. We must look around for any occurrence of capital Q. There's a capital Q here, and there's a capital Q here. So when we differentiate this new Hamiltonian with respect to capital Q, we have the partial derivative of that function, we simply call it h, partial q. And we have this, the chain rule tells us we have a multiplicative factor. So there's a 2 square root of p cosine from the derivative of that, cosine q. That's the first term, but we have another occurrence of capital Q. So we'll have a plus, there's a partial h, that's this function here, differentiating with respect to its second input, which is called lowercase p, right? That's the name of the second input. And by the chain rule, we multiply, there's a root 2p, and then we must differentiate the minus cosine. That's going to give us a minus sine. Okay, so you see where this is going. We have some more derivatives that we need to compute. Okay. But the crucial thing here to take away is that we're working in a much bigger space. We have canonical transformations, a huge class of functions of this form, and they preserve Hamilton's equations. Okay, so I'm going to stop the recording for today's lecture. We're going to continue this calculation. Okay, remember, when are we going to continue? We're going to continue tomorrow at 9 o'clock. And it's customary, UC Berkeley, we're going to add 10 minutes. So at 9:10 tomorrow, we'll continue this discussion. So with that, I'm going to stop the recording. I will stay here for questions.